All right, let's talk about 1.2. 1.2 is a little bit more information about computing limits. In this section, we're gonna start to develop some of the tools that we use for calculating limits a little bit more easily without having to make tables and graphs and things like that. And so we're going to start off with something that's that should be pretty intuitively clear. And by the way, you can go ahead and pause the video to write this stuff down if you want. But the first thing is that, okay, so first of all, let's say that a and k are real numbers. And if you're taking the limit as x approaches a of some constant term, well, that limit is just going to be that constant term, right? Because this function doesn't depend on x at all. So it doesn't matter what x is approaching. K is always just going to be k. So that's the first result, and that should be pretty intuitively clear. Another way to see this is if you were to graph this thing. So let's say that k is up here, right? This is just a horizontal line through k. So, and you know, so whatever a is, maybe a is this number here, but clearly the limit as x approaches a from either side is just going to be k, right? So, so that's that first one. And the second one says that the limit as x approaches a of x equals a. And that should also be fairly intuitively clear. So for the second case, the function you're interested in is just f of x equals x, which is this straight line right here, right? It's just the identity, right? So if this is a, then this also has to be a, right? If the input is a, the output is a, because it's just the function f of x equals x. So if the input is a, then the output is a, and so the limit as x approaches a is of course just going to be a. So to give you just a couple examples of this, limit as x approaches negative 25 of 3, well, that's just going to be 3, right? Because this function doesn't depend on x at all. 3 is always just going to be 3 regardless of what x is. Right? On the other hand, limit as x approaches negative 2 of x, now that's going to be negative 2, right? So those two results are going to come in handy. They're pretty useful. They're also pretty intuitive. It should be pretty clear that that is the case. So now the big theorem is this one. This is sort of the nuts and bolts of this section. So again, I would encourage you to write this down for sure. But so go ahead and give the video a pause if you need to and write down this theorem. I'm going to go through and explain in words what's going on here, because I know it looks like a lot of crazy symbols, but it's not as scary as it maybe looks. So first of all, let's say that a is a real number. If we're looking for the limit as x approaches, a of two functions, of the sum or the difference of two functions, we can distribute that limit. Okay, the limit distributes across the addition and subtraction. So if you had, you know, if f of x was just x and g of x was 7, then the limit as x approaches a of x plus 7 would be limit as x approaches a of x plus limit as x approaches a of 7, right? So the limit distributes across addition. That's really nice. The limit also, well, distributes across subtraction, but it also distributes across multiplication. So you can just distribute the limit across addition, subtraction, multiplication. Part D says that you can distribute the limit across division. So it behaves really, really nicely. Part C tells us that if you have some function being raised to the nth power, and you're taking the limit of that thing, well, what you can actually do is just take the limit of the function first and then raise the result to the nth power. And part E is saying something similar, right? Part E is saying that if you're taking the limit of the nth root of some function, you can actually move that limit inside of the radical. You can take the limit of the function first and then just take the nth root of that. So, in other words, limits behave really, really nicely. They distribute across just about every operation you can think of. we'll talk about some more later on in the semester, but this is good information to get us started. Quick note about parts D and E. So in part D, you can distribute the limit across the division provided that limit as x approaches a of g of x is not 0, right? Because if this thing is 0, then of course the division is undefined, right? So there is that kind of proviso, I guess. And then for part E, you can move the limit to the inside of the radical provided that the limit as x approaches a of f of x is positive whenever n is even, right? So that might require you to think back to algebra a little bit, right? But you may recall that, for example, the square root of a negative number is not a real number. And in this class, we're not going to be talking about complex numbers. That would be a topic of discussion for a complex analysis course in like upper division math. So we're just sticking to the real numbers for this course, right? So anyway, if we want this thing to be a real number and n is an even index, so if n is an even number, then your radicand needs to be positive. Now, if n is odd, then the radicand could still be negative, right? Like the square root of the cube root of -8 is just -2. That's still a real number. It's when you have square roots or fourth roots or sixth roots that you end up with problems. And so we require that the radicand here be positive if the index is even. Anyway, so that's that. Now, in each of these statements, I was using a two-sided limit. But actually, each of these statements is true for the one-sided limits as well. So instead of x approaching a, maybe we're only interested in approaching a from the right, or maybe we're only interested in approaching a from the left. These statements would still apply. Okay, these statements are still true for one-sided limits. Another thing that I will point out, an immediate consequence of all of this stuff is that if f of x is a polynomial, then the limit as x approaches a of f of x is just f of a. In other words, you calculate the limit just by plugging a in for x. And I'll show you an example of this. So for example, we have limit as x approaches 3 of x squared plus 2x minus 2. Now, using these things that were stated in the theorem, using those as facts that we know now, we can rewrite this. We can say, well, first of all, this limit is going to distribute across all of this addition and subtraction. So I can rewrite this as limit as x approaches 3 of x squared plus limit as x approaches 3 of 2x minus limit as x approaches 3 of 2, right? So I've just distributed the limit, right? So I just distributed the limit to each of these terms. Now, limit as x approaches 3 of x squared. I'm going to apply, so by the way, this was because of Theorem 2 part A that I'm able to do this, right? Now, part C tells us that this exponent here, I can take the limit as x approaches 3 of x and then just square the result. So in other words, because of part C, I can say that this is going to be limit as x approaches 3 of x squared. Limit as x approaches 3 of x all squared, like that. And similarly, here I can distribute the limit across this product. So I can say this is plus limit as x approaches 3 of 2 times limit as x approaches 3 of x. And finally, I still have minus limit as x approaches 3 of 2. So this was because of part C. This was actually because of part B. So maybe I should say B and C, right? Both of those, I used both of those facts. But now, we know that limit as x approaches a of x is just a. That's because of Theorem 1b, right? So because of Theorem 1b, I know that limit as x approaches 3 of x is just 3. So this is because of 1 part b. Now that I can say that this is 3 squared plus Oh, we also know limit as x approaches a of k is just k. So limit as x approaches 3 of 2 is just going to be 2. So this is plus 2 times 3 minus 2. So I guess this is because of one parts a and b. So a and b that I'm able to say this. But what you'll notice is that this is just exactly what I would have gotten if I had just gone ahead and replaced x with 3 from the very beginning. So what I'm trying to say is you can cut out all these middle steps, because really, taken together, what all of this stuff is saying is that whenever you've got a polynomial, you can find its limit by just plugging in the input value here, by just plugging in that number, right? And you can see that clearly here. Just for the sake of argument, we can finish this, right? 3 squared is 9, 2 times 3 is 8, that's 17, and 17 minus 2 is 15. So you should get 15 for that limit. Anyway, and it's pretty nice that you can conclude this without having to make a table or look at a graph or anything like that. Right? So that's pretty good. So with that in mind, let's go through a few more examples. So let's calculate some limits. Let's do limit as x approaches 5 of x squared minus 4x plus 3. Okay, go ahead and give the video a pause and work that out. Okay, here's my solution. This is a polynomial, so I can find this limit by just plugging in 5, right? I can just say this is 5 squared minus 4 times 5 plus 3. That's 25 minus 20, which is 5, plus 3, which is 8. So you get 8. Okay, here's another one. Limit as x approaches 1 of x to the 7th minus 2x to the 5th plus 1 to the 35th power. Ooh. Okay, go ahead and give it a pause, see if you can work this one out. Okay, so here's my solution. Again, this is another polynomial, no big deal. I'm going to plug in 1. I get 1 to the 7th minus 2 times 1 to the 5th plus 1. 1 to the 7th, or sorry, that whole thing is then raised to the 35th power, right? Okay. Anyway, 1 to the 7th is 1, 1 to the 5th is 1, so we have 1 minus 2 plus 1. That's just 0, right? That's just 0 to the 35th power. Fortunately for us, right, that's really easy to compute. That should just be 0. Okay, one more. Let's do limit as x approaches 2 of 5x cubed plus 4 divided by x minus 3. Now this one is not a polynomial, right? But you have Theorem 2 part D here, which says that you can just calculate the limit of the numerator and denominator independently of each other. And the numerator and denominator both happen to be polynomials. So in other words, you can calculate this limit by just plugging in 2 for x as well, provided that when you plug in 2 you don't get 0 in the denominator, which I don't think you do in this case. So give this a pause, see what you get. Okay, here's my solution. Two cubed is 8, 8 times 5 is 40, 40 plus 4 is 44, 2 minus 3 is negative 1, so I think you should get negative 44 as your final answer there. Okay, so that's all there is to Theorem 2, right? It's basically just telling us that under certain conditions, you can go ahead and plug in values, just plug in this value, and that's going to be what your limit is. Now, what we're going to focus on for the rest of the section is this proviso on part D. what happens if this limit is 0? Right? What happens if the denominator is 0? What do you do with that? So let's talk about that. So I'm going to give you a third theorem, and I haven't written this one out ahead of time, so you'll have to bear with me while you write this down. We'll write this down together. But so Theorem 3. Let f of x equal p of x over q of x. Be a rational function. So in other words, p and q are polynomials, right? And let's let a be a real number. Okay, so a couple things to say. So first of all, as we've already seen, as we saw in part C up here, right, if the denominator is not 0, right, if you plug in a for q and you get something that's not 0, so if q of a is not 0, then limit as x approaches a of f of x is just f of a, right? So if you don't get a 0 in the denominator when you plug in a, then that's your limit, right? That's your limit. But if q of a does equal 0, so if q of a does equal 0, and if p of a also equals 0, then x minus a is a common factor of p and q. All right, so if q of a is 0, so if the denominator is 0 but the numerator is also 0, then x minus a is a common factor of p and q. Now, what we can do with that then is we can factor out the x minus a from the numerator and the denominator, and then we can cancel it off. And after we've canceled it off, then we can try plugging in a again, and hopefully we end up with something like, hopefully that eliminates the problem in the denominator of getting 0 in the denominator. Okay, if it doesn't, then we burn that bridge when we come to it. But that's the strategy. So if p and q are both 0, so if the numerator and denominator are both 0 when you plug in a, then factor out an x minus a and cancel it. Okay, and then see what you have to work with, right? And maybe I should say, you know, if this is the case, if part B is the case, then the limit is whatever you get after you cancel off the common factor, whatever you get when you plug in a, right? That's going to be the limit. Okay. And then the third scenario is, it could be the case that q of a is 0, but that p of a is not 0. If that's the case, then the limit as x approaches a, well, x approaches a of f of x does not exist. Okay, so if you plug in a and you get something like 7 over 0, then automatically you know that the limit doesn't exist. We can be a little bit more specific than that, though. So in this third case, part C, there could be 3 possibilities, right? So it could be that the limit may be positive infinity. It could be that the limit may be negative infinity. Or another possibility is that the limit may be negative infinity from one side and positive infinity from the other. to figure out which of these cases is going on, we just have to make a table of values, right? So that's what we're going to do in case C, right? If we get something like, -5/0, then we know that the limit doesn't exist. But if we want to be more specific about which of these cases we have going on, we're going to make a table of values. Okay, so let's practice. I'm going to walk you through several examples here. And all of these examples are going to be really similar to each other. I do that on purpose so that you can hopefully really get a good understanding of what's going on. So let's calculate some limits. Let's do, first of all, limit as x approaches 2 of x plus 1 over x minus 3. So whenever we're approaching these kinds of limits, the first thing we're always going to try is we're always just going to try plugging this number in for x. And if we don't get 0 in the denominator, then we're golden, right? That's our answer. So if I plug in 2 for x in this case, I get 2 plus 1 over 2 minus 3. That's 3 over -1, which is just -3, and that's it. That's our limit. Okay? We didn't get a 0 in the denominator, so we're good. Let's look at another one. Let's look at limit as x approaches 2 of x plus 3 over x squared minus x minus 2. Now, on this problem, we don't have quite as much luck, right? Because when we try to plug in 2, we get 2 plus 3 over 2 squared minus 2 minus 2. That's going to be 5/0. Okay? Well, what does that tell us? That tells us that we're in a case C situation, right? Q of A is 0, right? The denominator is 0, but the numerator is not 0. So we know that the limit doesn't exist. Now, if we want to have a better understanding for it, okay, so we know that the limit doesn't exist, but is it shooting off to infinity? Is it shooting off to negative infinity? Or is one side going to negative infinity and the other side going to positive infinity? To figure that out, we have to make a table of values, right? So we'll make a table where we're approaching from the left, and then we'll make another table where we approach from the right. To see what's going on, and then you just do what we did in the previous section, right? 1.1. So we want to plug in values closer and closer to 2. If we're doing this from the left, then we might start at like 1.9, and then 1.99, and then 1.999, and then if we're approaching from the right, we might start at like 2.1, and then 2.01, and then 2.001, right? And then we can plug these values in to the function. So I'm going to do 1.9 plus 3 divided by 1.9 squared minus 1.9 minus 2. You should get about -16.8966. If I plug in 1.99, then I get -166.89, and I bet when I plug in 1.999, I'm going to get 1,000. Oh no, I get something very different. Oh no, I missed one. Sorry. Oh yeah, I do get what I thought. You get -1,666.89. So I think from the left, this is shooting off to negative infinity. I wonder what's happening from the right. If I plug in 2.1. Okay, so I get 16.4516. If I plug in 2.01, I get 166.445. I think I know where this is going. I feel like it's shooting off to positive infinity, right? So this is like this third case, right? One side is approaching negative infinity, the other is approaching positive infinity. So this limit we're just going to say this limit does not exist. So limit as x approaches 2 of x plus 3 over x squared minus x minus 2 does not exist. Okay, that's that. Okay, let me show you another one. So, very similar to the previous example, part C. Let's do limit as x approaches 2 of x minus 2 over x squared minus x minus 2. So that should be pretty familiar. Part B, the only thing that changed is the numerator. I changed it from x plus 3 to x minus 2. The reason I did that is so that we would see a case B scenario, right? Because notice that when we plug in 2 now, we get 0 over 0. So that is a case B scenario. And if you have a case B scenario, x minus a is going to be a common factor. Now in this case, a is 2. So I know that x minus 2 is a common factor of the numerator and denominator. So let's see if we can factor it. So I'm going to say limit as x approaches 2 of x minus 2 over x squared minus x minus 2. Clearly, we can't factor the numerator because it's already a linear polynomial, but the denominator we could factor. I think that this thing is x minus 2 times x plus 1. Okay. And now notice that the x minus 2's will cancel. You get limit as x approaches 2 of 1 over x plus 1. Now we can plug in 2, and if we don't get 0 in the denominator, then that's our limit, right? So we plug in 2, and we get 1 over 2 plus 1 is 3. And so that's that. Okay. Okay, let's look at another one. Let's do limit as x approaches 2 of x plus 1 over x squared minus x minus 2. Okay. Now, if we follow our strategy that we've been following, we would go ahead and plug in 2, and we would get 3 over 0, and that tells us that the limit's undefined. What I want to show you is that if you were to factor this, we saw earlier that this is just x minus 2 over x plus 1. So another thing that you could maybe think to do would be to do something like this. Then you can cancel off the x plus 1's and get limit as x approaches 2 of 1 over x minus 2. But notice that in this case, that doesn't really help you, because when you plug in 2, you're still going to get 1 over 0, which just tells you that the limit is undefined, or that the limit does not exist, right? So again, this is a case where you'd make a table of values. Whenever you have, so remember 1 over x, f of x equals 1 over x. This thing looks like this. Nope, it looks like this actually. Okay, that's what 1 over x looks like. So you're going to be approaching negative infinity from the left and positive infinity from the right. That's what's going on here. So we're just going to say limit as x approaches 2 of x plus 1 over x squared minus x minus 2 does not exist. Okay, you can make a table of values if you feel more comfortable doing that. But it's good to know what graphs look like. Okay, let me give you one more. Let's do x squared minus x minus 2, our old friend. Oh, sorry. I want to do limit as x approaches 2 of x squared minus x minus 2 over x squared minus 4x plus 4. I wonder what's going to happen here. Well, if I plug in 2, I have 2 squared minus 2 over 2 squared minus 4 times 2 plus 4. In the numerator, that's definitely going to give me 0. In the denominator, I'm going to have 4 minus 8 is negative 4 plus 4 is 0. I get a 0 over 0. Okay, so this is one that I have to try to factor, right? So I would do limit as x approaches 2. We've already seen the factorization of the numerator. It's x minus 2 times x plus 1. In the denominator, this thing factors as x minus 2 times x minus 2. So that's pretty cool. I can cancel off one of the x minus 2's. And I get limit as x approaches 2 of x plus 1 over x minus 2. Now when I plug in 2 here, I'm going to get 3 over 0. So I can't factor this any further, right? I'm getting a 3 over 0. So this just tells me that this limit is undefined. Okay? Or not undefined. I keep saying that. The limit doesn't exist. Right? So we'll just say limit as x approaches 2 of x squared minus x minus 2 over x squared minus 4x plus 4 does not exist. Okay? And again, you could make a table of values to see what's going on. This is another case where you're going to be approaching negative infinity from one direction and positive infinity from the other. You can take my word for that, or you can work it out on your own. It's up to you. So that's the strategy. Okay, so that's how this stuff works. You start off by just plugging the number in, and if it works out that you don't get 0 in the denominator, then you're done. If you do get a 0 in the denominator and you don't get a 0 in the numerator, then you make a table of values to see what's going on, right? If you're approaching negative infinity from one direction and positive infinity from the other, then we just say the limit doesn't exist. If you're approaching negative infinity from both directions, then you would say the limit is equal to negative infinity, right? And similarly for positive infinity. If you plug in the value and you get 0 over 0, well, then you try to factor. Cancel off common factors and then plug in the number again, and whatever you get the second time around, if you don't get 0 in the denominator, then that's the limit of the original problem. Okay? So that's the strategy for dealing with limits of rational expressions. One thing that I should say is that this 0 over 0 business turns out to be, pretty important, as you can see. So let's call it something. So I'm going to give you a definition now. A quotient f of x over g of x, in which f and g both have limits of 0 as x approaches a, is called an indeterminate form of type 0 over 0. So it's an indeterminate of type 0 over 0. Or I might say it's an indeterminate of the form 0 over 0, right? Something like that. Anyway, but the reason this is important is because as we saw with rational expressions, whenever you get an indeterminate of the form 0 over 0, you can oftentimes do some algebra, in this case factoring, to cancel off common terms, and then you can compute the limit directly after canceling off common terms. But it turns out that that's not only true for rational expressions, that's true for any indeterminate of the type 0 over 0. We can oftentimes do some kind of algebraic manipulation to figure out what that limit is. So let me give you an example of something that has a radical in it, right? That goes along these same lines. So example 4. Let's find the limit as x approaches 1 of x minus 1 over square root x minus 1. And we actually did this problem in the previous section, in section 1.1. We did it using a table of values, but I want to show you that you can do this algebraically without making a table of values. Notice that when you plug in 1, you get 0 over 0, right? So since this is an indeterminate of the type 0 over 0, that tells me that we can do some kind of algebraic manipulation to find this limit, to calculate this limit. If you got an indeterminate of the form, 5 over 0 or something like that, then you would know automatically that that this limit doesn't exist, right? But because it's a 0 over 0, the limit does in fact exist, and we can find it by doing some kind of algebraic manipulation. Now in this case, factoring is not really an option. But what you can do, and what you have probably seen before in algebra class, is that you can multiply by the conjugate, and that will clear any radicals that are in the denominator. So the conjugate in this case would be square root x plus 1. Right? The conjugate is always just the same thing, but switch the sign in the middle. So I'm going to multiply by that in both the numerator and the denominator. And let's see what we get. Okay, so in the numerator I'm going to have x times the square root of x. If I wanted to, I could think of x as square root of x as x to the 1/2 power. And then x to the first times x to the 1/2 would be x to the 3/2. I'm just gonna leave it x root x for now. And then I'm gonna have plus x minus root x minus 1. Let's see what happens in the denominator. I'm gonna have root x times root x. That's just x. Then I'm gonna have positive root x minus root x cancel, and then minus 1. So I just get x minus 1 in the denominator. So, well, that didn't really help, did it? I was thinking that that would do the trick, but it didn't really. We've got x root x plus, so nothing, If we plug in 1 now, we're going to get 1 plus 1 minus 1 minus 1, so that's going to be 0. We're still going to get a 0 over 0. That's interesting. Let me look into this. I'll pause and I'll come back when I figured it out. Okay, I figured it out. That was so silly of me. Whoops. So silly. So check it out. What I shouldn't have done is I shouldn't have distributed in the numerator. What I should have done is I should have just said, look, this is limit as x approaches 1. I'm just going to leave this x minus 1 times square root x plus 1. And then if I do distribute the denominator, though, I get x minus 1, as we saw earlier, right? And then you get to cancel the x minus 1, see? So that was my silly mistake. I'll make plenty of those throughout the semester, so you have to be patient with me. Anyway, so this is going to be limit as x approaches 1 of root x plus 1. Well, so if I plug in 1 there, I'm going to get square root 1 plus 1, which is just 2, right? So that's that. So that's a pretty common trick whenever you have radicals. You can try multiplying by the conjugate to clear them. So, so that's that one. Now I want to give you one more example. This one is going to be an example of a piecewise function. So for this one, let's say that f of x is defined piecewise as follows. So it's going to be 1 over x plus 2 if x is less than negative 2. It's going to be x squared minus 5 if x is between negative 2 and 3, including the 3, not including the negative 2. And then it's going to be square root of x plus 13 if x is greater than 3. Okay, so there's our function f. And here's what I want to find. So let's find, we'll do a few things. First of all, let's find the limit as x approaches negative 2 of f of x, if it exists. Okay, so in order to do this, remember, I have to look at the limit as we approach from both the left and from the right. So if I'm approaching from the left, so if I look at limit as x approaches negative 2 from the left, right, of f of x. If I'm approaching from the left, that means x is slightly less than negative 2, so I would be in the top case here. So I would use this function, right? So, and I would just plug in the negative 2. So I would get 1 over negative 2 plus 2. Well, that's 1 over 0, which tells us that the limit doesn't exist. But since this is just a one-sided limit, I can be more precise than that. Like I can say whether or not this thing is going to negative infinity or positive infinity. So to figure out where it's heading, let's just think through this. Rather than making a table formally, I'm just going to think through this in my mind. If I'm plugging in numbers less than negative 2, then like negative 2.1, for example, then I'm going to get negative 2.1 plus 2 is going to be a negative number, and 1 divided by a negative number is going to be negative, right? If I plug in negative 2.01, I'm still going to get a negative down here. So, so this thing it must be shooting off to negative infinity. So I'm going to say this thing is shooting off to negative infinity as we approach from the left. What's happening as we approach from the right, I wonder? If I'm approaching from the right, then that means I'm slightly bigger than negative 2, so I would be using the middle rule here. So the limit as x approaches negative 2 from the right is going to be negative 2 squared minus 5. That one's a little easier, right? Negative 2 squared is 4, and 4 minus 5 is negative 1. So the limit as we approach from the left is negative infinity, right? The limit as we approach from the right is negative 1. So therefore this limit does not exist, right? The two-sided limit does not exist because you're approaching different values from the two different sides. Okay, so that's the limit as x approaches negative 2. Let's look for the limit as x approaches 0. Of f of x, sorry. Limit as x approaches 0. Well, as x gets closer and closer to 0, 0 is between negative 2 and 3. So again, I'm going to be using this middle rule. And f doesn't change rules at x equals 0, right? I'm going to be using this middle rule whether I approach from the left or from the right. I'm going to be using the middle rule in either case. So I think I can just find this directly by saying this is just going to be 0 squared minus 5, which is negative 5. Okay, and that's all there is to part B. Part C, let's find limit as x approaches 3. Now this is a place where the function does change rules, right? It changes rules at x equals 3. So we have to be a little more careful. So let's look at what's happening as we approach from the left, and then we'll look at what's happening as we approach from the right. So if we're approaching from the left, that means x is slightly less than 3, so I would still be using the middle rule in this case, right? So I would say this is going to be 3 squared minus 5. That's 9 minus 5, which is 4. As we approach from the right, though, x is going to be slightly larger than 3, so I'm going to use the bottom rule. So it's going to be the square root of 3 plus 13. That's square root of 16, which is also 4. Ah, that's interesting, right? So the limit as we approach from the left is 4. The limit as we approach from the right is 4. That means the two-sided limit is 4, right? Because each of the one-sided limits is approaching the same value. So the two-sided limit is equal to that value as well. Okay, so this is how we would deal with piecewise functions, right? If you're looking for a limit as x approaches some value where the function changes rules, like at -2 and 3 in this case, then you need to look at what's happening as you approach from the left and what's happening as you approach from the right. Okay, but that will do it for this section. So we'll see you in the next one.